All right, hey there, calculus students. We are here today to talk about Euler's method. Leonhard Euler was a Swiss mathematician in the 1700s who did a lot of really important work. Definitely, if you're interested in the history of mathematics, he's a guy that really made his mark. The big thing that I know that you of what you've seen is the fact that we use the letter E in order to represent the natural number, or that 2.718 number that we use with like natural logs and things like that. He was a big pioneer in using that relationship, and he was the first one to call it E, or so the story goes. All right, so I know it looks like Euler, but it is pronounced Euler. That's the way that I've always heard it from other people who are smarter than me, so I usually trust them. But here we go. So we're going to be talking about using Euler's method to approximate solutions to differential equations. So I've got a warm-up right here with a couple of integrals for you. So if you want to pause the video and try these out yourself, I would encourage you to do that. And then I'm just going to go ahead and solve them. So hopefully you paused and you did your work yourself, but here we go. So this is a u sub right here. If we let our u equal our radicand, our derivative would be 2. And I need a 2, so I'm going to put in my 2 and I'm going to put in my 1/2 to offset it. And then when I think about what the pattern is here, what I have is 1/2 the integral of u to the 1/2 power du. And that's going to give me a 1/2. I'm going to add 1 u to the 3/2 reciprocal 2/3 plus a constant. So my actual result, let's see, this is going to be 1/2 of 2/3 is 1/3. My u was, of course, my 2x minus 3 to the 3/2 power, plus, of course, my constant of integration. Okay, for the second one here, this was one that you may or may. So the first thing I'm just going to kick the 4 out. I don't need that 4 to be there. And then we know the derivative of secant x, how it's secant x tangent x. But we did spend a day going over the antiderivative of it. I'm not going to go through the proof of it. Please feel free to check your notes. It was section, I believe, 4.7 where we covered that. It was in December, so feel free to look back at that. But this one is going to come out to 4, and this is the one that's ln absolute value secant x plus tangent x plus a constant. So we still get that secant x tangent x thing kind of pattern I'm dealing with, but it is ln absolute value secant x plus tangent x is going to be the antiderivative of our secant x dx plus our constant, and then with our 4 multiplier. Right. All right, so hopefully that was a good start to our topic for today. So here's my wording here. You've got this written out. You can read it for yourself, but I'll read it with you here. So Euler's method is a numerical approach to approximating the particular solution of a differential equation. As you can see, we've created, I've got a nice little diagram right here, right. Here's the actual function, here's the actual curve, and then this is what Euler's method uses to approximate. Basically what we're doing, we're taking a known point, that's our first point right there, I've labeled it as a sub 0, and then using the slope and the previous point repeatedly to kind of, from here, the tangent line, right, the derivative, told me it was going in this direction, and that gave me to this approximate value. Look, it's pretty close. And then we kind of reassess. From this point right here, we look at the slope of the tangent again. Oh, it's not quite as steep, so we adjust it. Boom, and that's going to take us to our next kind of intermediate location. And then still a pretty good approximation, right? And then from here, right, here's our approximation. We take the slope of the tangent again, boom, and that's going to kind of balance us off here, and then again we can kind of keep repeatedly doing this. Basically what we're doing here, and that's what I've said right here, we're going to multiply the slope at each intermediate step by that horizontal distance, and kind of work our way across in order to get a new y value, and use that y value in the slope to get a new y value, and use that y value in the slope and to get a new y value. And so it's just repeated calculation of what we've got. Okay, so I've kind of got it summarized right here as far as kind of formulaically, if you would. So if we start at x sub 0, y sub 0 as our general overall starting point, and then what we're going to do is we're going to go to the next point in the step, and I'm going to label that as x sub 1, y sub 1. Okay, so to get x sub 1, what we're going to do is we're going to take that original x value and add whatever that horizontal, that step size, to it. So the x's are really easy, because each time I just need to add that step size. It's kind of like that delta x concept when we're talking about working with Riemann sums or working with a lot of other things that we've done. But that consistent kind of delta x, or h in this case is the way that I've labeled it. And then the y's is where the actual calculation is going to happen. So what we're going to do for the y's is we're going to take the previous y value. So when I'm at y1, when I want y1, I'm going to take y0. I'm going to take the original y value, and I'm going to add it to my horizontal distance, my step size, okay, times the differential equation with the previous point substituted in. So you'll see y sub 0 shows up originally here, and then it's also potentially going to get substituted in to the differential equation. So it's the differential equation with the x and y value as they are into that differential equation. Multiply that by h and add that to the previous y value. And that's going to give us our new y value. Okay, so once again, we're going to take that previous y value, we're going to add our h, our step size, our horizontal distance, our delta x, if you will, and multiply that by the differential equation with the specific x and y value from the previous step, right? X sub 0, y sub 0, in this case, the originals. And then it's just repeating that process. And then we're going to repeat that process. To get to x2, we're going to go one more step size, one more horizontal distance from x1. To get to y2, now what we're going to do is we're going to use that previous point, the values that we got for x1 and y1. The previous point, we're going to start with the y value that we just got. We're going to add h times, and then again, the same differential equation. But this time we're going to use the previous point, not the original points, not the x0, y0 from the original. We're going to use the ones that we just got in the previous line right above us. And if I wanted to keep going, I could do x3, keeping the pattern, and y3, keeping the pattern going. So we can do this on for any number. Usually on the AP test, it's usually 2 to 4 steps. Usually. Often 2, honestly. Often these are pretty short. They're actually not that bad. Our textbook, I actually don't like the questions in our textbook because they often do them as 10 steps. And it's like, oh my god, it's so tedious. So much more than what's actually needed. Okay, so that's Euler's method. So basically what we're going to do is we're going to get our starting point, which is going to be given to us. And then we're going to figure out our step size. Sometimes they just explicitly tell you the step size. And sometimes they give you enough hints that you can figure it out. And I'll show you kind of the difference between those. Okay, so I've got 2 examples for you to work through. Okay, so here's the first example. Okay, let y equals f of x be the solution to the differential equation. We don't know what that is, but that's what we're referring to. So f of x is our solution, our antiderivative, if you will, of this differential equation. As you can see, this one has a differential equation of 1 plus 2y. So we only need the y value to do the differential equation in this particular case. We've got the initial condition f of 0 is equal to 1. So this is essentially like our x0, y0. This is our starting point. Our x value of 0, our y value of 1. And then we're finding the approximation for f of 1. F of 1. So we're starting at f of 0. We're going to f of 1. We're going to use Euler's method. We're going to start at x equals 0 because that's the information we have. And this time it flat out tells us the step size. So now we know the step size, or what I was referring to as the h value, the horizontal distance. Right? So we know h is going to be 0.5. And then we just want to kind of set ourselves up. So what I like to do to organize my information. I like to start with my x value, right? If I have an x value of 0, I have a y value of 1. I got that right here, right? This is my x value, this is my y value from my initial starting point. So that's kind of like my x sub 0, y sub 0. And then we know that our step size is going to be 0.5. So if my x is, I'm going to add 0.5 to it. So x is 0.5. It's going to be my next one. So this is kind of like my x2, or my x1 rather. We'll tell you what, let me do it. Let me put in that. Let me just be consistent. Okay? If I call this my x1, to find my y1, what we're going to do is we're going to take our original y value, our previous y value, which in this case is 1. We're going to add to it the h, right, the delta x, the change in x, 0.5 times. And then the key here is that inside what we're going to multiply this step size by is the differential equation. We're going to do 1 plus 2y. And the y value we're going to be getting is going to be that previous y value. So that previous y value, right here, I'll do a highlighter for you. That previous y value is going to go in 2 places in this case, here and here, because we've got it as our starting point, and then we've also got it as our multiplier on our horizontal distance, on our step size, because y was a part of the differential equation. Okay, then we just need to do some calculating here. Let's see, this is 1 plus 2, that's 3. 3 times a half is 1.5. 1.5 plus 1 is 2.5. So this comes out to 2.5. So my intermediate step now, the y value at this intermediate step, when x is 0.5, the y value I'm getting from Euler's method is 2.5. So this is my new approximation. Okay? Again, this is not an equal sign, right? This is, well, it is an equal sign, but it's not equal to our actual function. It's really close, though. It is an approximation. So if we continue the pattern, x2, we're going to add another 0.5. In this case, that's going to take us to 1. And that's actually our stopping point. That's what we're looking for. We're looking for f of 1. So this is the x value that we needed. So to get to my next y value, we're going to take the previous y value. Okay, let me do a different highlighter here. How about a orange highlighter for this one? Perfect. Okay, so this 2.5, right, the previous y value is going to be where we're going to start from, plus, again, 0.5, our horizontal distance, and then we're going to have our, again, our differential equation, 1 plus 2y, 1 plus 2, and then the y value this time, again, is not the original y value, but the previous y value. So that previous y value goes here and here, just like the previous y value from this step went here and here, 2.5. Okay, and then we just want to calculate that. 2.5 plus, let's see, this is 0.5, okay, plus 1 plus, well, 2 times 2.5 is 5, right? 2 times 2.5 is 5. 5 plus 1 is 6. Half of 6 is 3, so what this ends up being is 2.5 plus 3, or in other words, 5 and 5/10. 5.5 is the value that we get. And so after, in this case, 2 steps of size 0.5, we were able to arrive at our kind of end point here. And what we can say is, we can kind of conclude that, okay, f of 1, which is what we were looking to approximate. Remember, this is an approximation, so I would definitely want you to be putting approximately equal to signs. And then our value here would be 5.5 and 5/10. Okay, it won't always be 2 steps, but a lot of the times on the AP test it is 2 or 3 steps, or maybe 4 steps at the most. So there you go. There's our first example. Okay, and it's just a repeated process. A repeated process. Okay, so let's do our second example. Worded a little bit differently. A lot of it's the same, right? Let y equals f of x be the solution. This is the way the AP test often writes them. Okay, so let's see. Okay, here's our differential equation. Let me underline this. Okay. Which is x minus y this time. So this time it's going to be a little bit different because we've got an x and a y in our differential equation. So now we're going to be using both of the previous coordinates. Last time we only had to use the y because remember our differential equation only had a y in it. This time there's an x and a y. Okay. Initial condition is f of 1 equals 3. So again, here's my starting x and here's my starting y. So I'm going to label, I could start that, x, 0, it's 1, y sub 0, right, my starting y value is going to be 3. Okay, so there's my starting. And then this time it's worded a little bit differently. It says, what's the approximation for f of 2? So we're going from f of 1 to f of 2. Okay, so I know that my total distance is going to be, total distance that we're going to go is going to be 2 minus 1. Right? So I'm starting at 1 and going 2. So in other words, my distance is 1. And I'm going to do 2 steps of equal length. So this one, it doesn't tell us exactly the size the way last time it explicitly said, hey, the step size. This time they're saying, hey, there's 2 steps of equal length. Well, if my total distance is 1, and I'm looking at 2 steps, then I'm going to take that 1 and I'm going to divide it in half. So my h value is going to be 1/2 again, or in other words, 0.5. It's not always, but many of the examples that I have found do them as 0.5s. Sometimes, well, if you want to look at the ones in the book, they do them by 0.1s and they do a whole bunch of steps, but like I said, this is more like how they ask the questions on the AP test. So let's get it. Okay, so I've got my starting location here, right? X0 and Y0. We figured out that our h value, or our horizontal change, or our delta x effectively, is going to be 0.5 again. So I know that my next x value is going to be 1 plus 1/2, or 1.5 is a fine way of doing it. And then for my y, my new y value, okay, we got our previous y value, So we're going to start with this. We're going to get our 3 right here, right? So it always starts from that previous y value plus our h, or our delta x, or our horizontal distance, times, and then this time it's going to be this x minus y thing. This time it's x minus y. So in here, remember last time we had 1 plus 2 times a thing because it was 1 plus 2y. This time we're going to get something minus something. But what it is, it's going to be the previous x, the previous line's x. So the previous line was 1 and 3, and x minus y, so 1 minus 3. Okay, once again, that 3 was the same 3 right here and right here. And then the 1 was the x value. This one right here came from this location right here. Right? Because that's our x value, our previous x value minus our previous y value right here. That's what we're using for our intermediate approximation. Okay, I'm just gonna do a new line for this one just to do, let's see, this is 0.5 times 1 minus 3, that's -2. -2 times 0.5 is half of -2, that's -1. So we've got 3 plus -1, or in other words, 2 is the result. 2 is the new y value where we're at. So our new coordinate point, our intermediate coordinate point, we started at 1, 3, now we're at 1.5, 2. Okay? We wanted to get to f of 2, so we need an x value of 2 now. So if I keep going, x2 in this case is 2. And to get my y, my corresponding y value, we're going to use our previous value, okay, our previous y value. So here's our starting, 2, right, here's our previous y value, 2, okay, 2. And then we're going to do the same thing that we did, right, plus our horizontal distance, that 0.5. And then here, we're going to have our x minus y, but we're going to get our x and y, again, from the previous step. So let me grab, hopefully you like the highlighting that I'm doing here. I'm trying to help you see the connection. Here's a new color. Okay, so x, here's my previous x, here's my previous y. So what we're going to get here is going to be x minus y. So 1.5 minus 2, and again, that 1.5 came from the previous point, and the 2 came from the previous point's y value. Okay, very colorful notes today for me. I just wanted to make sure that you could kind of see where those numbers come from. That x minus y from the previous line, the x and the y from the previous. Boom. The x and the y here, again, came from the previous. Okay, so if we calculate out what we have here, let's see, this is 1.5 minus 2. That's negative 0.5. and then times another 0.5. So this is 2 plus 0.5 times negative 0.5. This is 0.25, right? This is so 2 minus 0.25, and that's going to lead us to a value of 1.75. 1 and 75 hundredths is what we would get here for our final approximation with Euler's method. And so our answer, again, is f of 2 is what we were looking for. So f of 2 can be approximated as this value that we got with our, in this case, again, 2 steps of equal length in this particular case. So we can write our result as f of 2 is equal to approximately 1.75. All right, so couple things that I want to make sure that you understand. It's not always 0.5. My 2 examples had it, but the work that you're going to be doing, they will vary a little bit. And it's not always 2 steps. It's not always 2 steps, but it often is. They're usually not too overly tedious because it is just this repeated pattern over and over. All right, so I made a worksheet for you guys, and hopefully that was enough to get you started on it. Yeah, best of luck, and I will see you soon.